And happy Sunday. This is PFG Live. And I'm Spencer Webb, and this is New Hampshire, where the current temperature is 61 degrees and the sky is cloudy. Welcome aboard, everybody. Let's see, we have lots of people in the chat already. We got Josh in southern Manitoba reporting out of Charlie X-Ray Mike Delta. Winds are 270 at 0 knots, temperature 182.03. And stuff. DBX, very close to White Plains, New York, is reporting winds variable at 6 knots, 10-mile visibility, broken at 3,500, temperature 2.13, altimeter 29.98. Warren Jones in Sutton, New Hampshire, reports 65 degrees Fahrenheit, mostly cloudy, calm winds, calm demeanor, and the lawnmower fired right up after the winter's rest, and I hate trucks. Well, welcome aboard, Warren. It's like everything's steady. Also, WidgetWorks is reporting 7 degrees science and rain, 81% relative humidity in Edmonton, Alberta, Canuckistan. Welcome, sir. Evils, in a appropriate font, reports something like 24.2 degrees science, 14.0 degrees dew point, 53.7% relative humidity. The pressure is 1,000. He's got pressure. And welcome. And Josh, our audio checker, says that the audio is check. Thank you very much, Josh. Let's see. Also, what else we got? We have in YouTube chat, we have CJ Stevens reporting 77 and a beautiful sunny day in East Tennessee. Welcome, sir. Currently preparing to get our meat birds to be ready for freezer camp. I'm sure you will enjoy it more than they will. K-Bonk is reporting 74 and cloudy, cleaning shop in the Philadelphia of the Pennsylvania, and he's copying us 5 by 5. Thank you, sir. Art That Makes Art West says there is a whole bunch of wind passing through south central Idaho today. It's 53 degrees Fahrenheit. And the onions are shaking. Joel L says 90 degrees. Joel L. Joel L, by the way, is my filament tester. Joel L says it's 90 degrees Fahrenheit, 8% relative humidity in Chandler, Arizona. Welcome, Joel. John Thawley is reporting 67 degrees and partly cloudy with a delightful spring breeze in Orange County, California this morning. Perfect garage cleaning weather. Welcome, Orange County. Nice to have you here. Carl says 58 and cloudy in the People's Republic of Rhode Island. And Carl is playing with both hands here because he's also in the Discord. Joel just reported it updated to 92 degrees in Chandler, Arizona. Let's see. At Manchester Airport, which is right up the street from me here, let's see. The winds are 060 at 7 knots, visibility 10 miles, overcast at 1,400 feet, temperature 17, dew point 12, altimeter 3004. Remarks are unimportant. And Tuck is here from the Buffalo of New York, 76 degrees and sunny in Buffalo. Welcome. Well, how is everybody? Last Sunday was Mother's Day, and as you know, I knew what was good for me, so we punted, and we're back. So it was a good time, and Mom's doing well. Thank you very much for those who asked. And busy week of client work. Busy week keeping the robots running. So I got to get my acronyms right. The SLA robots were running. The FDM robots were running. The grinder, which is a material subtractor, was running. Oh, a shout out. I don't want to give his name because I don't have permission to do that. But I got an order for PFG Stones, which I think earned the most diverse order ever that I've received. Basically, this company, this gentleman, ordered the menu, but wait, there's more. He got bevels. he got custom laser marking. The only thing on the menu that was not ordered on this order was lips on the PFG Stones. So if you don't know what I'm talking about, head over to pfgstones.com when we're done here today and learn all about it. But that kept me very busy on the grinder. The grinder just did not stop all week. Machine New Zealand has shown up. Good morning to you, sir. 8 degrees C and cloudy in New Zealand. Welcome aboard. I always have to figure out what time it is for you. Let's see. Today's Sunday. So you have to go to work in a couple hours, right? Or maybe less than a couple hours. Ugly Skull has shown up, reporting from the Philippines. 26 degrees science, partly cloudy skies, and rain showers. Welcome, Ugly Skull. Well, I think we've covered the globe. We have control of the entire Earth now. We could do whatever we want. So welcome, guys. And in Discord, yes, you have to go to work shortly at 6:05 a.m. He's living in the future. We're lucky to have him. In the Discord, we have Evils, Carl Tauber, Warren Jones, DBX, Widgetworks, Josh, Tucker, and Thomas Hardy. Welcome to Discord. An apt name for this group. So, as many of you know, I had a very interesting week, and I visited FormLabs, and I believe since we, I don't remember the spacing between the two visits, but it was 2 good visits. And in the thumbnail for this video, which is actually up on the screen, Chase Cabron was my host, and he's awesome. He met me on both visits and took care of me. I made a new friend. He's a good guy. And he's also been invited to come on the PFG.Live at some point to talk about some inside baseball about FormLabs. So I have been making product on the FormLabs printer in the shape of the noses, right? So here's a nos. Actually, we have a couple of noses here. I will explain why we have 2 noses in a second. But these 2 guys were critical in the last 10 days. And these, you might recognize that these are noses that go on the small, lock line equivalent. And if you don't know what a nos is, information is at noz.gg, noz.gg. So the Form 3 has been great. And let me just explain to you a little bit about how these printers work. A resin printer, not everybody knows what resin printing is, but you literally are curing liquid resin and then moving a work surface up as the layers cure to make your parts. And when I started designing the NOS, first I had to figure out how I was going to make it. So that was going to be resin printing. So I got involved with FormLabs. FormLabs has resin printers and they make their own resins. So it's a vertically oriented, it's a walled garden. It's like the Apple of resin printing. So it took me a while to figure out how to make the NOS because it has some mechanical requirements. It has to have a snap action over the ball of the coolant line. Well, I started with the original resin that they get you going on the FormLabs machines, which is called Gray version 4. Very descriptive because it is gray and it is version 4. So the first noses I made would crack trying to push it over the ball. And I went down this engineering rabbit hole of adjusting the sizes and putting slots and stress relief, things in there to try to get this to work. And then I finally came to the conclusion that, gee, maybe one of the 25 other resins that they make is the appropriate resin. And of course, that was the answer. So I switched over to the resin which I've been using and I have fallen in love with, called Tough 1500. Tough 1500, and I like the way they do this, because on their data sheets, they pretty well tell you this is an analog to polypropylene. So if you've ever done anything with plastic and you kind of know that you're holding polypropylene, you know what I'm talking about. It's the plastic that if you jammed your thumbnail into, you can kind of mark it, and it's got a little pliability. Well, that was the answer. As soon as I started making these out of Tough 1500, they started snapping together like nobody's business. It was perfect. So that went along for quite a while. I've been making and selling the noses that are printed on the Form 3 Plus with Tough 1500, and it works great. If you're not running a business, it's expensive. The printers are expensive, the resin is expensive, but boy howdy does it work, and it does exactly what it's advertised to do. Along comes the Form 4 printer. So, 2-3 years worth of the Form 3 Plus, and the Form 4 comes out. And I think I talked about it last time, and it's a complete departure from what they were doing. And I won't get into the architecture of the machine, because that's not why we're here. But it's fast. It's 3 to 5 times faster than the Form 3. So I basically got on the horn with FormLabs, and I met the guy you saw on your screen, Chase Cabron, and set up a meeting to go down to FormLabs. Now, I recognize that I am fortunate in that I'm under an hour away from FormLabs, and it's on the way to Boston. So I was able to go down easily and put hands on and showed you guys some pictures on Instagram and learn a lot about it. The speed was interesting to me, and we'll talk about why in a second. It's the big thing they changed. However, there are other things that changed in the machine that were kind of interesting. They changed the form factor of the work bed, so it's now instead of being square, it's now a rectangle. So in one dimension, you actually get a little more space. That was cool. And some other nice things. And then the second visit I went down, I basically was ready to make the buy decision on the Form 4. But I said to myself, okay, we've got to set some gates that they have to get through before I actually place the order. One of the gates was I'm sending you models. I want you to print them and hand them to me before I give you an order. So between the first visit and the second visit, they printed 3 different models for me. One of the 3 different models was this NOS, okay? And functionally, in all aspects, it is absolutely as good as what the Form 3 was. In some cosmetic areas, it's a little nicer. There were 2 variables that changed, right? When you do an experiment, you like to change one variable and see what happens. Well, the one variable I wanted to change was which machine it was made on. Well, it turns out that they did slightly reformulate the resin, the Tough 1500, for the Form 4. It's all good. It's all positive. I looked at this thing and it was glorious. And there were 2 other prints, one of which we're going to talk about today and one of which we're not going to talk about today, which they also printed for me. And they were excellent. So to make a long story short, I pushed the button and placed the order. So it's coming. The visit was great, watching the Form 4 run at light speed. And we did a hard calculation. We'd say sliced, right? We sliced the NOS, and it was an honest 3x speed up in production at no sacrifice of quality. So that's pretty good. So you got to sacrifice something. Well, you sacrifice more shekels, okay, because the Form 4 is more expensive. But it's not crazy more expensive, but it's more expensive. So that was all a big, hairy win, and we had a good time. So the Form 4 is on the way, and when I get it, we'll show it and talk about it and do all that kind of stuff. So that was the FormLabs visit. Very, very positive. But wait, there's more. So during this whole episode, I get a message from someone who says, "Hey, I hear you're going, to visit FormLabs. You should come see my shop." So in my mind, I'm like, oh, they mean that they have a shop somewhere in Somerville, Massachusetts. By the way, every student who ever goes to school in Boston is required to live in Somerville, Massachusetts. So I said, sure, tell me more, and we get hooked up on email. It turns out, no, it's the guy that runs the shop at FormLabs. So then a neuron fires in my brain, and I remember that indeed FormLabs is a customer for PFG Stones. This gets better. Hang on. So the guy who runs the shop, his name is Franco, and he is awesome. Hi, Franco. I know you're listening. And Will is also in the shop there. So those two guys were great to meet. So I go down there, and after my visit, Chase walks me over to the shop, and we go visit the shop, and I get the full tour. So they have some really nice machines, and I did not take pictures, but I asked if we can come back for a shop tour, and they said, yeah, let's do it. So we will have a shop tour. They have a great big Mazak 20 by 40 VMC. They have a great old Brown and Sharp Micromaster right up my alley that was sitting there running while we were there. Let's see. Oh, and I saw the first laser welder. It looks like a MIG welder, but it's lasers. The first one I've ever put my hands on. And they were using it in prototyping and building stuff in the lab. That was really cool. More on another date. Hey, I want to say hi to Test Room 2003. He says, checking in late from Oostkapelle, Netherlands, 19 degrees C and 72% relative humidity. Welcome aboard, sir. So the shop tour was great. And of course, while we're doing the shop tour, Franco goes over and pulls out his PFG Stones. So just for the record, he had a set of round 4-inch aluminum oxide PFG Stones. And he knows how to use them, and they were using them in the shop, and they asked a few questions. And Will had been working on a right angle that he bought off of, I'm not sure if he bought it off eBay or what, but it was a Suburban tool. Probably came, as machined, and then he ground it. So he brought it over, and he wanted me to weigh in on what I thought about his grinding job. Well, his grinding job was actually very, very good. And then one of the things I did with these guys, and I find myself doing this a lot with PFG Stone customers, is, people are kind of very gentle with them. And I was like, no, you could put a little pressure on them and go. So I kind of showed them how I would attack the surface. And sure enough, the surface after PFG stoning gives up its secrets, and we're able to see some fine detail that told us about how the grinding was. And frankly, the grinding was really, really quite good. So that was kind of fun. And then I told these guys, I said, do you know that PFG stones are made on custom work holding? And the custom work holding has parts in it that are made on my FormLabs printer. So Franco buys the PFG stones And now he's making parts for FormLabs printers. And then I'm buying the printers to make the parts for the work holding for the PFG Stones. It's a complete circle. True story. So that was a ton of fun. So that's the story on the FormLabs. I am selling my FormLabs 3. I don't really want to ship it. So I will either sell it or I will donate it to an educational institution. That might happen. We'll see. The third possibility is that I keep it as an occasional use machine, as a backup, whatever. I don't know. But it's a great machine, and we'll see what happens. So that's the story on FormLabs. As always, if anybody has any questions in the chat, feel free asynchronously to just pop it in the chat, and we'll try to get to it. So that was a good time. Let's see. I don't have any pictures. Like I said, I didn't take any pictures while I was there, so that's kind of too bad. So then I get and I asked permission, by the way, to discuss this project, and I got permission. So just so you don't get too worried about this, I get this message from John Grimsmo. Now I'm a big fan of John's work. Here's a saga, which is on my desk always, and John says, I'm thinking of getting the bearing cages for the knives resin printed or printed, but I think we got right to resin printing. And he said, I wonder if you'd be interested in trying to prototype this for us. And of course I said, yes, I would be interested. It's a very interesting engineering problem. So I started figuring out how to do this. And as you can see on your screen, is the part we call P11, or the 11th prototype. And I have landed on this and said, this is it. So actually, as I speak, I have a full build plate of these running downstairs, and we could talk some more about that. Evils has figured out that we could put PFG Grimsmo on there. Yeah, we can't do that. Don't cross the streams, dude. So this is how I keep track of all of the prototypes. This is like a plastic divider box, and this is where all the P's went. And it was a very interesting problem, because when I looked at this, I kind of said, and John and I talked about this a little bit. We could print this thing flat on the bed of the printer, but it turns out that this thing is really teeny. So if you look at your screen, you'll see this thing is really small. Okay. And the act of trying to print it flat on the bed was, I'm not going to get into all the details, but it was really hard to do. We did try it, and we may revisit it. So it was printed fairly conventionally for SLA printing, using supports tilted at an angle, and getting the supports right was the hard part, because this is teeny. But finally we arrived at P11, and we hit the button, and we're making a bunch of these things. In the picture on your screen, those balls that are in there are 1/16 of an inch diameter, just to give you an idea. And they snap into this bearing cage. So we tried a couple of different resins, as usual. Yes, WidgetWorks, we will explain the reason for the angle printing, no problem. When I printed this out of gray resin, baby's first resin, the PLA of resins, and sure enough, when you try to snap a ball in, it cracked, it shattered. Not super unusual, but of course, the first thing that goes through my mind is, oh, I've solved this problem before. So we started making them out of tough 1500. What do you know? They start snapping in quite nicely. So the balls snapping in, the maintenance of dimensions were both outstanding. In fact, John gave me a dimension for the center hole that had to pass a pin through it, and we actually added 1/1000th of an inch to that diameter of the inner hole, and it was absolutely measurable with gauge pins on the versions after which we made that adjustment. So dimensions we had. Then came, how do you support this thing? So there's sort of no getting away from marks. I just changed the picture here. So you can see some little features on the back, which were the result of the support arms. And this is resin printing. This is how it works. But those are really manageable and easy to clean up. If you go up to the software, and in the FormLabs world, the software is called Preform. And if you go to Preform and you just throw your part in it, there is a magic wand that you could hit, and you could tell it, please just do everything you need to do to print this part. And it will orient the part, build supports, put a raft under it, or even print it directly to the platen if that's what you tell it to do. It depends on the part. And say, here you go. Hit print and I'll print it. And for simple things, that works. However, this isn't simple because it's so teeny. And I quickly learned that the thin spots at the periphery of the balls and the periphery of the part are thin, and they're not very strong. And if you sit there and put a great big honking support there and you try to break the support off or even cut the support off, you're going to damage it. So that was one of the issues. So automatic, like software, yeah, I got this, here's your supports, doesn't work. So I had to manually, and I've been doing this for almost all of my parts. I have to manually put the supports in, make some decisions, decide the size of the support contact, which is one of the choices you have to make, and get the strategy, the support strategy to work. So WidgetWorks asks, why the angle? Why don't you print it flat? So when you print on an SLA machine, the support structure, the build plate goes down, and then the light paints a layer. So the first layer is like on the build plate, and then it moves up, and then it comes back down, except for one layer's worth, which is 0.05 millimeters in this case. And then it prints the next layer, and then it pulls up. Well, in the pulling up, it actually has to remove that layer from the bottom of the reservoir, which is where it gets cured. FormLabs has some techniques for very low force removal of that layer. That's kind of what they pride themselves on. However, it's really thin and it's really delicate. So you have to get that print started very carefully and build up a little bit of structure, and then it's pretty strong, and then you can keep going. So if you try to print this thing like horizontally, for example, just lay it horizontally, still on supports, but horizontally, eventually comes a layer where the whole bottom gets printed at once. And that's the first layer. And it's very delicate, but it's very big in area. And now you try to peel that off the plate. It doesn't matter how low force your peel is, it's a problem. So you tend to tilt it up so that the contact point as you build it up is tiny, and then a little bigger, and then a little bigger, and then a little bigger, and that's what you get from the angle. What angle do you use? It's not obvious. Some parts, you put them vertical, you tilt them over 15 degrees or 20 degrees, and you're done. This part was not one of those. I believe I ended up at 45 degrees for reasons, but it's not a hard and fast rule. The build plate, well, we have to define terms here. The build plate that you're thinking of is the metal plate. Let me throw that picture back up. So here's what the what we would call the build plate. That it is flexible or not is not important. The bottom of the reservoir is a piece of plastic film, frequently FEP, and that has to be flexible to allow the layers to peel off and then come down to get ready for the next layer to be cured. That's the layer that we're worried about. And that has to be flexible. And the strategy of getting the newly cured layer off of it, because you literally cure a layer on that FEP sheet. That's what the bottom of the reservoir is. In the Form 3, it had a really cool way of peeling it. I don't think I'm going to get into the details. In the Form 4, they have a slightly different approach, but it's still a really cool way of peeling the bottom of the FEP off of the part that you're printing. So I hope I'm explaining that sufficiently so that you understand what the problem is. Yeah, we may have to have a whole show on this. Maybe that's a good excuse to bring somebody from FormLabs on. But even if you're using a $300, Elegoo printer off of, your favorite purchasing site, it's the same problem. And they solve it in different ways. I think FormLabs has nailed it. And the big difference between the Form 4 and every other printer on the market that looks like the Form 4, okay, has a light source on the bottom, has an LCD, has a build surface, has a tank, has a build plate that goes down into the tank. The difference is that they went step by step to each stage and just engineered the heck out of it. It's very impressive. And it works. So that's the story on the Grimsmo bearing cages. They work very well. AB Shop is here. Welcome, sir. Good morning from Alberto of AB Shop from Venice, Italy, where it is 20 degrees C and sunny. Sounds very standard. Welcome, sir. So I then, once we got P11 done, and oh, by the way, I'm making 5 of these things at a time to evaluate. And then once I thought, by the way, I thought P10 was it. And it had a couple little things at the bottom, at the launch point, okay? And when I say bottom, I mean bottom of the part. In the real world, it would be the top. And it had a couple of little things, and I'm like, it's good enough. And I showed it to John. John's like, yeah, it's close enough. But then when I started making them in quantity and I got statistical information, some of them were just not coming out at all. And I actually printed a 70 of the P10s and tossed them. In fact, I did a post on Instagram. You might have seen it today. And then I quickly went to P11. I prototyped 5 more and confirmed, oh yeah, now we have it, right? It was that last little to get that thing right. And then we're printing, we're actually on the second plate full of P11s, and they look awesome. So I'll be sending those up to John. His team will be removing the supports and proceeding ahead. And I will also point out that I am not inserting balls. That's not my job. And the stuff that he uses in the knives is not 52-100 bearing balls. They use a very special, very wicked cool bearing ball, which I think is ceramic. I don't remember. Maybe somebody can fill me in on that. Let me see if I can get your question. Joel says, I assume you also get thicker part cross sections for each pull. Yeah, you start tiny and then they don't get thicker. They get bigger. So the part is building up. So now it's stronger. Machine NZ confirms, yes, ceramic. Thank you. And that's the thing. When you're designing it, you have to imagine what's going on. What's the process? Yeah, Joel, right. They get wider, right? And they're getting stronger. And once they're nice and strong, you can use fewer supports, right? The part is its own support. But until you get to that, you have to be very thoughtful about how you apply supports. I want lots of supports for strength, stability. I don't want lots of supports because I have to remove them. So there's the tug of war. And I went through that, obviously. P11 tells you the whole story until we got it to where it is. Machine NZ says, out of interest, what are John's bearing cages made out of presently? Presently, they're made out of Delrin, which is a pretty close analog to the Tough 1500 resin. And they're made on the Swiss lathe. So, John's argument to me is I'm tying up a $400,000 Swiss lathe. If we can make these at high quality using an SLA process, I get to free up that machine, and he needs to free up that machine. That was the argument. Excellent argument. And I think we've arrived. I think we got there. And I think he'll be able to use these cages to do what he has to do. Couple of important points. These are not high velocity cages, right? This is literally as the blade opens and closes. The cage has the balls in the holes, as you see it on your screen. They rattle. They have clearance. So the cage itself is not adding anything to the friction. And they look fantastic. We'll find out from John, because if they're going up to Canada, and if John says they're good, they're good. If John says they're bad, it's back to the drawing board. So we'll see what happens. Evil says, did the cages change? Last I heard they're machined from POM on his Swiss, or is that for a different product? I don't think I know what POM is, but I believe it's Delrin. Oh, he says disregard. Okay, there you go. Acetal, Delrin, POM. Okay, we're talking the same language. Yes, all the same. Yeah, it's Delrin or acetal. Sorry, I shouldn't. Delrin is a registered trademark, and acetal resin is the correct term of art, and POM is half of a pom-pom. Okay, I think we answered that question. Yes, K-Bond correctly observes, he says, damn, that must be small attachment points on SLA. Yes, it is. So the very first support, this is for you SLA guys, the very first support is actually a reasonably beefy support point. It's the first size of support point that the software doesn't like say, hey, whoa, dude, caution. And then I start using smaller support points as best I can. How thick is the cage? Oh, you had to ask me that. You know what? I'm going to guess. It looks like it's about in freedom units. Well, it's got to be less than a 16th, right? I'm going to guess that that's about 050. Yeah. monopolymer versus copolymer. I don't know. Let's see. Okay, I see Tuck. Did you have a question, Tuck? No. Okay. So this could be a win. And the very big point here for Grimsmo is, where do you put your high horsepower capability, especially with respect to precision? Do you put that into a non-precision part? Also a cosmetic part. I think if John was here, he'd argue that it's still a cosmetic part because his knife customers are going to open up their knives and they're going to see it. Well, I get that. But boy, SLA has been pretty awesome. And this, Machinist NZ says he's off to work. Hey, dude, thanks for being here. I appreciate you. We'll see you. Say hello to the other side of the world. I see a raised hand. So let's bring Tuck in for a question. Let's see.
Hey.
Tuck from Buffalo, New York. You're on the air. Hello.
Excellent. Hello. Thank you for taking my question. So for the bearing cages, is it a straight through hole or is it slightly spherical to retain the ball bearing? As you said, they snap in.
Yes, you are correct. It is a spherical. It is a section of a spherical hole, because otherwise you couldn't get it.
Excellent.
Yeah, the sides are curved, right? And that's why it snaps in and then it rattles around, but it doesn't leave. You are correct.
Very cool. Thank you.
You're very welcome. Take care and good luck. We're all counting on you. My sound guy was on it today. So, yeah, that was an excellent question. K-Bonk says, I run into problems with multi-part SLA build plates. Good luck. Well, I will share, what I learned. This has been it's been a pretty linear engineering path with respect to getting this part from an idea, hey, let's make this part out of SLA, to we're making this part out of SLA. Obviously, 11 prototypes. Frustrated. Carl. Carl named it. He says, so the holes are frustrated spheres. Thank you, sir. You are correct. Conjet says, hello. Would a waffle delivery be welcome? Actually, no. You can come say hello, but I can't eat right now because I'd be eating. Robin says, if the races are flat, making each hole a slightly different radius would increase the fatigue life by a factor of 10. Let's think this through because I'm trying to understand it. And then I might force you to come on, Robin. If the races are flat, got it. So the races are the parts that the balls ride on, okay? Making each hole a slightly different radius would increase the fatigue life by a factor of 10. Okay, I think I see it, Robin. So what you're saying is, by giving the balls an opportunity to not always be in exactly the same track, you are reducing the fatigue life. Maybe saying it a different way. Oh, different radius. Now I got it. I may still bring you on. So what you're saying is, if you give half the balls one track to ride in and then half the balls another track to ride in, you are at least doubling the fatigue life, probably more because it's not linear. Did I get that right? I'm waiting. When you're waiting for Robin, it's the most tense time. It's almost as tense as getting a waffle delivery. Robin says yes. Okay, got it. So that's a message for John, in that that's a great idea. Instead of one train track, have multiple train tracks. We got a visit from Conjet. Hi, Conjet.
Hi.
You mean you could have brought me a waffle?
Half a waffle.
By the way, I want to point out that we have some syrup here for the waffle, which I'm now pouring on Kanja's head.
Oh no! I've been tarred.
Do you like that?
That's awesome.
We'll get to that in a minute.
What?
Robin.
What is that?
Robin knows what this is.
That's mildly terrifying.
Doesn't it look like syrup for the waffles?
Live taste test.
Thanks for visiting.
Yeah, I wanted to come say hi.
Okay.
No waffle this time.
No, I'd be sitting here eating. Maybe afterwards.
Afterwards.
Maybe in the after show. Because in the after show, these guys don't mind if I'm chewing. All right. Talk to you later.
Love you.
Okay, Robin. Stand by, Robin. Somewhere in Pennsylvania. Hello, you're on the air.
So the ideal way to adjust those radii are to do the Hertzian stress calculations for the actual width of the contact patch close to the permanent deformation stress level. In other words, the ball, especially when you're using ceramic balls, even though they sound neat, the problem with them is they're so much harder than the races that those races will Brunel sooner with the ceramic balls than they would with 440C or 52-100, because the balls are not conforming. They have such a higher, they're so much stiffer that they don't squish and spread the contact area out as well. So I'm not telling John he shouldn't be using ceramic balls, because the advantage of them is there's no possibility of metal to metal welding. So they have the advantage of they can run without lubrication, and you will not get any kind of metal transfer or asperities that are welding together. So that's an advantage of them. So I'm not dissing the ceramic, other than the fact you have to be cognizant that they will Brunel the races quicker. So you do the contact stress things, and you can get what some of the other Hertzian calculations are. What's the actual patch width at X pressure, and what are the compressive stresses? Do that, and you can say, okay, give each ball, and if it's a limited range arc of motion, then which this is, you could even have them where certain balls go through, I don't know, well, this is almost 180. So yeah, for all intents and purposes, you get the point. The radii would need to be varied by that much. And then what that boils down to is fatigue life wise, each of those tracks as it's being exercised has its own. It's not 10 balls riding on that same track, Bruneling it. So that's the point.
Excellent point. I too am not judging John's balls, but I will point out what? I will point out that you teach us correctly that everything is rubber, right? So in an ideal world, and this is sort of an explainer here, in an ideal world, if you took a flat surface, I happen to have a flat surface here, and you took a ball and you put it on that flat surface, you would literally be contacting it at a point. That in the ideal world, but everything's rubber, so the race is going to deform elastically, the ball's going to deform elastically, and you end up with an area of contact, which you're calling a contact patch, and
right.
And the calculations,
and
the calculations to get there are the Hertzian calculations,
right? And so the beach ball and mattress analogy gives you an idea of what's going on there. The ball's conforming, the mattress is conforming, and they both comply. That's why when you go from the beach ball to a basketball, which is the ceramic ball is doing next to no deformation. Therefore, the amount of force to Brunel will be immensely less with the ceramic ball. And if you listen to the BOM,
Business,
broadcast, John and John.
business of
Many
machining. Just
business machine.
Just to give them a proper plug, the Business of Machining podcast with John and John. That's what you're talking about with BOM. Yeah. Okay.
John talks a lot in the development of the knives. A lot of his problems are Brinelling, meaning which part is yielding and denting, and so that's a constant battle and some of those things can be simple as changing the curvature. Very small balls are intensely, and sometimes a pin with a immensely larger radius than the ball, even though harder to make, can radically reduce those. So having those people that are engineering this kind of stuff should have those calculations plugged into Excel or a programmable calculator, where you can back solve for any of those things and instantly just plug in your numbers. And once you do that, then you can forget even what they're called. You know what to do. Oh, this much pressure, these two contact radii or flat to plane, whatever, cylinders. I have those on my 48 HP, and it just lets you go and say, okay, what is this? Otherwise, you'll just never do it. Oh, it's too laborious, and then you make mistakes 15 times, missing things. So it pays to get them in. It's very helpful if you engineer that stuff.
Hey, can we get a spreadsheet together that we could share with everyone? Would that be hard to do?
I'm not. I do calculations on Excel, but I know it can do back solving. With whatever variable you want to back solve for. I haven't exercised that aspect of Excel.
I know how
my calculator does it.
Let's work together, because I know what you're doing on the 48. And I think that might be a cool thing to make available to the community and say, look, this is this is what's really going on. And we could talk about that some more. But thank you for your insightful input.
There on the NIST site is a contact stress calculation ready to go, that has those things for gauging purposes. And so it might be just us getting that link. I have the link for it. I'll send it to you. And I think that might just do it just as easily. Just go on the NIST site and and do that.
Yeah, man.
That's more gauging oriented than universal, but still applicable.
I like it. That throws some light into an area that's kind of mysterious for many folk, current company included. Well, thanks. I appreciate it. And come again. We'll see you in the after show. All right. Thank you, Robin. So WidgetWorks asks, isn't it the Bill of Materials podcast? No, it's not. Although I do give them grief about that. Let's see. Evil says you'd have to offset the balls by more than the wiggle room each ball has, so the two closest tracks don't merge into one. I'm not sure if there's enough room for that. Yes. So we have a problem here. We have an engineering design of a product, and we have no clue what everything around it looks like. John has 700 variables in his head. So we don't know. The answer is we don't know. And it's a good question. WidgetWorks says, so do it correct the first time saves time and money? Robin needs to come teach oil field engineers. You mean they just throw stuff at the wall and see what sticks? Is that what you're trying to tell us? That's really funny. Anyway, well, that brings it full circle. So there's a story on making these bearing cages. Here's the good news. The cage guy, by the way, I was given the design of the cage. I didn't design the cage. I made little teeny adjustments, but that's about it. But the cage guy's making cages, and let's see if the customer's happy. That's what's coming up next week. And just between you and me, the customer has to get the knife show, okay? Let's just remember that. Let's see. Did we clear? Oh, Almost Machining is here. Almost. Welcome aboard, sir. Nice to see you. And by definition, you cannot be late to the PFG Live as long as you are PFG and as long as you're alive, that's fine. So let's talk a little bit about self-checking gauges. Stand by, Robin. So we're going to do a thought experiment, a Gestalt experiment, as Einstein called it, to understand why. Actually, I'm glad you're here, Robin. There's something you did a while ago I'm going to have questions about. Why you can have a self-checking gauge, and what some simple ones are. We're not going to go super deep, but the reason I bring this up, I bet you think this sounds like a complete non sequitur, doesn't have anything to do with anything. When I was at the FormLabs shop, the guys asked me that. They said, how would you measure perpendicularity? And we got into this whole discussion. And of course, I suggested that they make a cylinder square. Gedanken experiment. Thank you very much. Not Gestalt. Gedanken. Thank you. If Einstein was here, he would slap me in the head, but that's okay. So the guys asked me how to measure perpendicularity, and I started talking them through, hey, make your own cylinder square. You got everything here you need to make a cylinder square. So that led me to thinking about, because a cylinder square is self-checking, other gauges. So let's start with a flat surface, okay? And this is probably the hardest one to get your head around. We need flat. We got to start in the world of making measurements. We need to start with flat. So for the moment, let's start with a bowling ball. And what I want you to do is stand on a bowling ball. Okay, I'm just looking at it. Spencer R just checked in, member of the Spencer tribe. He says he just caught up to the live. You should check out Hertz Win by Vink Systems for the Hertz contact calculator. That's HERTZWIN. Hertz Win by Vink Systems for the Hertz contact calculator. Thank you. We'll look it up. Meanwhile, you're still standing on this bowling ball, right? Do you know you're standing on a bowling ball? Of course you do. Is it hard? Yeah, you kind of going to fall off the bowling ball because it has a very high curvature and you're trying to stand on it and you're not used to that sort of thing. And you look down and you say, I'm standing on a bowling ball. Now let's take the experiment to the next stage. Let's have you stand on something that is a sphere of about 100-foot diameter. Okay. Can you stand on let's say it's a dome on top of an educational institution. Just saying. Okay. Imagine the dome at MIT and you're standing on the dome. Can you stand on the dome? Yes. Are you relatively stable? Yes. Do you know you're still on a dome? You could kind of sense that you're still on something that's, on the order of hundreds of feet in diameter. Excellent. Now let's take that sphere and make it the size of planet Earth. Guess what you think? You think it's flat, but it's not flat. It's got a curve to it and it's got a radius of curvature, and the radius of curvature is getting bigger and bigger and bigger. And at infinite radius of curvature, your surface is flat. But of course, in the real world, nothing's flat. So if I said to you, here's a surface, I want you to measure how flat it is, you have some work to do. Now, let's assume for the moment that it is a smooth surface. It only has a first order curvature, okay? CJ Stevens reminds us to hit those likes and subscribes before heading out. Thank you, sir. And have fun. So if you went to measure the radius of curvature of something, let's say you walked up to your surface plate and we told you that this surface plate has a radius of curvature and nothing else. So there's no other dinkuses, there's no other little wiggles or anything. How would you measure flat? So one of the things we do is we run around with an indicator on an indicator stand, and we measure with our indicator 5 inches away from our indicator stand, and we run around, and if the reading doesn't change, we say it's flat. But in reality, what it says is it is spherical. We didn't measure flat. We measured that it's spherical. Okay? So, how can you measure something so that you are actually measuring the radius of curvature? And you want to know that it's essentially infinite, or deviation from flat is 0. We said the same thing. One way you could do it is by having a twist gauge that's 2 points of contact, and in the middle we put an indicator. Okay, we run around with that. We observe it never changes, and now we flip it over and we run around with that. And if we get the same number when we flip it over, okay, then we say it's flat. But that's not a trivial thing to do. And Robin, a while back, made such a gauge. Am I right, Robin? Yes? Okay. And the concept is, again, let's break it down as a thought experiment. Take a pin and a third pin, okay? And we set that down on our surface plate. If all 3 of those pins are exactly the same length, okay, and now we flip it over, all 3 will contact the surface plate, okay? 3 pins, they all contact, flip it over, 3 pins, they haven't moved with respect to each other, they all contact. And of course, they're attached to an inflexible plate. Now, you have just measured for flatness, okay? That gauge, because you've used another method to measure the pins' lengths, which is actually fairly straightforward to do, as you can imagine, now you've measured for flat. But we almost never do that, unless you're Robin, in which case you designed a really cool instrument. And I'm going to ask Robin to come back on and just ask a few questions. We're not going to spend too much time on this, but Robin, you're on the air. So
that's the rensometer.
I would say rensometer.
Rensometer. Okay.
So you made one out of a carbon fiber plate. Is that correct? And then
yes,
you had your 3 pins, and then the center pin was being measured by an electronic gauge.
Yeah, the center, the 2 outer the 2 outer gauging surfaces are the same height. They're attached to the beam rigidly, but the center leg, which is also the same length from pad to pad, is on a flexure, carbon flexure, and that's measured by an LVD I, similar to an LVDT, but it's inductance, not voltage variation from that. It's the gauge heads that are in the Brown & Sharp 981 units. So that measures that, and there's a whole bunch of things design-wise relative to making it accurate, as in unidirectional graphite and using the almost 0 coefficient of expansion properties of that, and a bunch of other things. But basically, if you can easily measure the height of the carbide pads that are on there, you can not easily, but you can lap them all to be the same height very exactly. And then when you reverse this, it's kind of like having a straight edge that you can reverse but has a measuring element in the middle. So it eliminates the problems of reversal that you can do with straight edges that take multiple ways of doing it.
But I would call
yes, it can measure.
I would call that a self-checking instrument, because
yes,
right, because
it requires no master to set it. And the whole property here is you You put it on, you have your electronic amplifier connected to this LVDI in the center. You put it on, settles out, you zero your meter, you flip it over, and it has special little knobs on the end, so you're not touching it at all. They poke it out where you can easily flip it over, put it back down again, seat it. When you whatever that measurement is, let's say it's 10 microinches, you dial your electronic 0 to 5 microinches, and now you're directly reading exactly straightness from either side.
So this is a good thought experiment. I mean, you're solving real practical problems in stiffness, thermal issues, and all that stuff, which we cannot be bothered with in a Goduncan experiment. But we have, I liked your definition of a self-checking gauge, is that it's one that does not require a master. So everybody can go out and build within some error band one of these to get to flat. Is that a fair thing to say?
Yeah, depending on, yeah, there's a lot of immense amount of things involved in if you're trying to get to be able to match what an autocollimator does or a laser does, which was my purpose.
Yeah. And then I wanted to move from flat onto perpendicular. So there's a bunch of ways to get to perpendicular, but if you had for example, two little angle plates on your surface plate and you put them together, if they had a blackout fit, and you were able to turn one around, see, that's the problem. You can't turn one around. But if you had a cylinder square and you walked up to your cylinder square with a right angle and you got a blackout fit, and now you went around to the 180 degrees to the other side of your cylinder square and you got a blackout fit, you have perpendicularity. And then the question is, well, how do you get the cylinder square? Well, a cylinder square, you start with flat, you make a cylinder, you measure your cylinder with your distance measuring tool, which we're assuming. And if everywhere you measure on the cylinder, top to bottom, rotate, top to bottom, if it all measures the same, I think we can agree it's a cylinder. Then, how do you know your cylinder is perpendicular to the base? And here's the magic of a cylinder square. And you stop me if I'm wrong, Robin. It doesn't matter, because if you make a measurement on one side and you go around 180 degrees and you make the measurement on the other side and the measurement flips in sign to the other side of 0, then you just measured 0. You average it, basically, effectively. Another feature of a cylinder square is if you rotate it, let's say it's leaning over, right? And you rotate it, eventually you'll find a rotation where your measurement top to bottom actually looks perpendicular, and you could mark it. So even though your cylinder square is leaning over, you can get square out of it. And of course you could bring it back to square once you've done that. So I would argue that a cylinder square is a self-checking gauge. Would you agree?
There's a lot of problems with a cylinder square.
Okay. What's the top one?
Okay. Well, I suggest a square block that you do the same procedures with, that has flat surfaces that you can check with an optical flat, and you can measure their parallelism much easier.
Mm-hmm.
And the problem with a cylinder square is your squareness checking device. Just the example you used where you rotate the square around till you get the same reading on both sides. The problem with that is it's leaning one direction, and now your spherical tip that you're measuring with is not the same location as the base, where the base was touching on the other sides. Yeah. So there's an error there from it leaning, mm-hmm. and all those things.
You're imagining using a squareness comparator. I'm imagining just an angle, an angle plate. That's the difference.
But I'm assuming we want to get past the precision level that you can do by visual light gap and all those things. We want to get to the point where we need a indicator that measures in sub tenth.
But really, the higher level question, and this is the argument, is: do you need an external master to achieve perpendicular? And I think the answer
No,
is
and you don't need a flat surface either.
it's nice to have one.
You only need you only need a concave surface for the example that you had there, so that the part does not rock,
Mm-hmm.
and you don't move the part from its location on the plate or the gauge. You rotate it and keep it in place. All you need is a stable support of the base that does not change the tilt of the part. That's why it needs to be concave.
Mm-hmm.
And the other thing, it literally could just be a piece of scrap iron. You could put 3 pads that the cylinder square sat on with feet to keep it centered, and go around and do it with nothing but that the 3 pads are defining the plane.
Okay.
And the cylinder square is sitting on it.
So those are 2 examples of self-checking gauges. You now have a way to get to flat and a way to get to perpendicular. And you never had to walk up to the master perpendicular gauge. Is there another? Can you come up with another example as a closing salvo here for a self-checking gauge?
I'm jumping to mine at the moment, but
yeah. Well, we did it. Those were the 2 I thought were very important, and it's worth studying from the good book.
it has lots of examples in there.
Yeah.
Of everything we just talked.
Yeah, this is the book, Foundations of Mechanical Accuracy by Wayne Moore. Yes, that Moore, and it's available from Moore Special Tool for $150 last time I bought it. It's sitting on my shelf. And I'm not saying that there's a PDF of it floating around. I didn't say that. So thanks, Robin. I appreciate you being here and allowing me to take advantage of it. Talk to you later.
Thanks.
Okay. We did it. It's past the top of the hour, but you guys are awesome. We had a lot to talk about today. I aim to have a guest next week. We'll see how that works out. I might have a guest the week after that. We have a couple of people in the queue. Thanks for tuning in. If you need some PFG Stones, go to pfgstones.com. The entire library of PFG Lives are available at, I know this is crazy, PFG.Live. Don't forget to like and subscribe. Thank you, CJ Stevens, for reminding me. And we'll see you guys next week. Same bat time, same bat channel. And remember, get flat and stay flat. And we'll see you next week.